right? So in today's class, I'm going to discuss about the various forms of antenna arrays, right? So very important, right? So definitely you'll get one question from this topic. So there are different forms of antenna arrays, right? Broadside array. So this is broadside array, end-fire array, collinear array, and parasitic array, right? Broadside array, end-fire array, collinear array, and parasitic array. So throughout the chapter, right, for linear arrays, I will discuss broadside array and end-fire array, right? How to draw the broadside radiation pattern and how to draw the end-fire radiation pattern, right? So initially I will give the definitions. What is broadside array, what is end-fire array, collinear array, and parasitic array, right? And all those definitions I will give you, right? So coming to broadside array, um, and the types of array are classified based on how antennas in an array are arranged, right? How antennas in an array are arranged. So coming to broadside array, in broadside array, number of identical parallel antennas, identical, right? Identical antennas. So identical antennas in the sense linear. So we are discussing only linear arrays, right? So not planar arrays or conformal arrays. We are discussing linear arrays, right? So therefore, identical parallel antennas are set up perpendicularly to the axis of the array. This is very important. Identical parallel antennas. Identical antennas in the sense what? All are of same type. Right? For example, if array contains four number of elements or four number of antennas, all four number of antennas are of same type. Right? In the sense one, they are dipole antennas. All four antennas dipole antennas, or all four antennas are parabolic reflector antennas. All four antennas are horn antennas, like that, right? All same type of antennas we use in the array, and they are set up perpendicular to the axis of the array, right? They are set up perpendicular to the axis of the array, right? So for example here, let us say this is the axis of the array, right? So this is the axis of the array, axis of the array, right? So in the axis of the array, just for understanding, I will take dipole antennas, right? So this is the axis of the array. Antennas are connected perpendicular, right? Antennas are arranged perpendicular to the axis of the array, like this, to the axis of the array. So this is antenna 1 and 2, 3 and 4, right? So all four dipoles are arranged perpendicular to the axis of the antennas, and all these antennas are parallel, right? So this antenna, antenna 3 and antenna 4 are parallel to each other. They are connected perpendicular to the axis of the array. They are connected perpendicular to the axis of the array, right? And that is one important point to be remembered, right? And second point, identical antennas are equally spaced, right? Equally spaced. That means what? The spacing between these two is d, and between these two is d, and between these two is d. Equal spacing, right? For example, d is equal to lambda by 4. That means what? The spacing between the elements is lambda by 4. If d is equal to lambda by 2, the spacing between the elements is lambda by 2, like that, right? So therefore, identical antennas set up perpendicular to the axis of the antenna is the first point. Each identical antennas are equally spaced is the second point to be remembered. And the third important point is all the elements are fed with equal magnitude and in the same phase, right? Excitation amplitudes, right? Excitation amplitudes, excitation amplitudes are equal, right? Are equal, and they are in phase, right? They are in phase. So equal amplitude and in phase currents, right? And that is the arrangement in broadside array, right? So if the array is like this, that means one, all parallel antennas are set up perpendicular to the axis of the array. That is the first one. And second one, equal spacing between the elements, and excitation amplitudes are equal, and they are in phase. If all these three conditions satisfies, then the radiation pattern is perpendicular to the line of the array axis and is bidirectional, right? And is bidirectional, right? So as shown in the figure, so this type of radiation pattern you will get, right? So this is the axis of the array, right? Axis of the array, and this is the radiation pattern you will get. And radiation pattern is perpendicular to the axis of the array, right? Perpendicular to the axis of the array, right? So that means what? If this is 0 degrees and this one is 90 degrees, and downward is 270 degrees, perpendicular to the axis of the array, and is bidirectional, right? Is bidirectional in the sense radiates in this direction and as well as in this direction. Bidirectionally it radiates, right? And that is called as the broadside array, right? So therefore in broadside array, parallel antennas connected perpendicular to the axis of the array, and equal amplitude, equal phase, and radiation pattern is perpendicular to the axis of the array and is bidirectional. That is broadside array, right? And coming to end-fire array. So end-fire array is exactly opposite, right? End-fire array is exactly opposite. Arrangement is same. So in not broadside array, it is end-fire array, right? End-fire. So in end-fire array, number of identical parallel antennas are set up perpendicular to the axis of the array, right? Same as in a broadside array, right? Same as in broadside array, right? So in broadside array also, this is the axis, right? And antennas are arranged perpendicular to the axis of the array, and like this. So this is the axis of the array, right? Axis of the array, and antennas are arranged perpendicularly, right? Antennas are arranged perpendicular, same as in broadside array. Then what is the difference? Here each identical antennas are equally spaced, same, equally. Spacing is also same, right? So equal spacing between, right? So equal spacing between the elements. And here comes the difference: equal magnitude out of phase currents, right? Equal magnitude in broadside array also, equal amplitude, and here out of phase currents. In broadside array in phase, and whereas in end-fire array out of phase, right? So therefore only one thing we have changed, right? Only one thing we have changed. What we have changed? We have changed phase, right? Broadside array in phase and end-fire array out of phase, right? Just by changing phase, the radiation pattern will become like this, right? So this type of radiation pattern you will get. So this is the axis of the array. This is the axis of the array, and the radiation pattern is maximum along the axis, right? Is maximum along the axis, and is unidirectional radiation pattern, right? We will obtain a unidirectional radiation pattern, right? So this is about the end-fire array, right? So therefore the only difference between broadside array and end-fire array is excitation phases. In broadside array they are in phase, and whereas in end-fire array they are out of phase. That is only the difference between broadside array and end fire array, right? And coming to the third one, collinear array. So collinear array consists of two or more half-wave dipoles, right? Two or more half-wave dipoles which are placed end to end. Here we are changing arrangement also. In collinear array, we are changing arrangement also, right? Two or more half-wave dipoles which are placed end to end, right? Which are placed end to end, and like this. For example, um, this is one antenna, antenna 1, and another antenna is connected like this. Another antenna is connected like this, and another antenna is connected like this. So this is called as end to end, right? End to end. So this is antenna 1, antenna 2, and antenna 3. So therefore all the antennas are connected end to end in a single line, right? In a single line. So therefore in collinear array we are changing the arrangement also, right? We are changing the arrangement also. And the maximum radiation in these arrays is broadside, right? Maximum radiation in this array is broadside. Broadside in the sense what? This is the axis, right? So this is the axis of the array. So this is the axis of the array, and radiation pattern is like this, perpendicular to the axis, right? Radiation pattern is broadside. That means perpendicular to the line of the array, like this, right? Bidirectional radiation pattern you will get, right? And collinear array operate in this frequency range, 30 megahertz through 30 megahertz to 3 gigahertz. That means what? VHF and UHF bands, right? And radiation pattern is perpendicular as shown, right? So as shown in the figure, radiation pattern is perpendicular, right? So excitation amplitudes and phases are same as in broadside array, right? Same as in broadside. That means equal amplitude and in phase currents in collinear array, right? So that is about collinear array. And fourth one, parasitic array, right? Parasitic array. So parasitic array which depends on the other's feed, right? Which depends on the other feed, right? So, for example, if you want to understand more clearly, right? Let me explain like this. Yagi-Uda antenna, right? I will take the Yagi-Uda antenna as an example to explain parasitic array, right? So I hope every one of you have seen the antenna, right? Yagi-Uda antenna, you know the Yagi-Uda antenna, right? I'm drawing the structure here. So this is called the Yagi-Uda antenna, right? And this is excitation, right? Antenna is excited like this, right? So this is excitation, right? And this is called as a reflector. This is called as reflector, and these are called as directors. So this is Yagi-Uda antenna, right? So in Yagi-Uda antenna, which contains, this is a dipole, and this is another dipole, and this is another dipole, and this is another dipole, and this one is called as the folded dipole, right? So this is called folded dipole because dipole is folded, right? Dipole is folded, therefore this is called as a folded dipole, right? So in Yagi-Uda antenna, it consists of one folded dipole and few dipoles, one folded dipole and few dipoles, right? And folded dipole is excited, only folded dipole is excited, and all the other elements are connected mutually. Only folded dipole is excited and all the other elements are connected mutually, and that is called as a parasitic array, right? So that is called as parasitic array. Only one element in the array is excited and all the other elements are connected mutually. That is called as parasitic array, right? So all the elements are positioned so that they lie in the induction field of the driven element, right? So in Yagoda antenna, the driven element is folded dipole, right? And it is operated in the frequency range of 2 megahertz to several gigahertz. And the example is Yagoda antenna, as I have shown just now, right? So this is about different types of antenna arrays, right? So we have four forms of antenna arrays. Number one, broadside array. Number two, end-fire array, and three, collinear array, and fourth one is parasitic array. Broadside array. So in broadside array, all the elements in the array are connected perpendicular to the axis of the antenna with equal spacing between the elements, and the excitation amplitudes phases are same, and the radiation pattern is perpendicular to the axis of the array. And coming to end-fire array, all the elements in the array are connected perpendicular to the axis of the array, just as in broadside array, and with equal spacing between the elements, equal amplitude, and out of phase. The only difference between broadside array and end-fire array is phase, right? In broadside array it is in phase, and whereas in end-fire array it is out of phase. And radiation pattern is along the axis of the array, whereas in broadside array radiation pattern is perpendicular, but in end-fire array radiation pattern is along the axis of the array. That is the main difference. And collinear array, antennas in the array are connected end to end, right? With equal amplitude and in phase currents. The radiation pattern is perpendicular to the axis of the array. And parasitic array, in parasitic array only one element is excited and all the other elements are connected mutually, and that is called as a parasitic array. And one best example is Yagoda antenna, right? So with this we have completed different forms of antenna arrays, right? So in the coming topics, we are going to discuss the array antenna. Initially I will take two element array, right? So once you know how to draw the radiation pattern of two element array, right, then it will become easy to understand the n number of elements, right? And two element array in the sense what? Array contains only two antennas, right? Array contains only two antennas. And one more thing is, in antenna array what we are going to do is we are going to find out the array factor. That's it, right? In all the topics throughout the third chapter, whatever the array you take, it may be 2 element array, or it may be 4 element array, or it may be 8 element array, or it may be n element array. What we are going to do is we will find out the array factor. Array factor in the sense what? Expression for electric field. E theta component we will determine. That's it, right? E theta we will determine. Why E theta? Because we learned in our previous chapter, I have discussed it, right? In far field region, only E theta and H pi components will be present. In far field region, E theta and H pi components will be present, and we have drawn the radiation pattern, and we have determined the directivity, and we have determined the beam area, gain, effective aperture, whatever the antenna parameter is there, we have determined those antenna parameters by using what? Electric field component, right? By using electric field component. So therefore we will derive electric field component, that is theta component, right? Theta component of electric field we will derive in antenna array, and which is called as array factor, right? So once we know array factor, we can draw the radiation pattern very easily. That is what we are going to do in our coming classes, right? So with this I will close and